Hello mathematicians, we're now going to have a look at stationary points and turning points. So stationary points occur wherever the slope of the curve, which is the same as we know as the slope of the tangent to the curve, is zero. So we've encountered this concept already. But stationary points can be of three types. They can either be local maxima or a local maximum, local minima, or horizontal inflection points. So we're pretty familiar, I hope, with the concept of a local maximum. It's where the function reaches its maximum value, which is where the slope of the tangent is zero. And leading up to that, which means coming from the left, from the more negative end of the number line, we have positive slopes, and past that point we have negative slopes. For a local minimum, then again, where the slope of the tangent is zero, and leading up to that we have a negative slope, and past that we have a positive slope. But for horizontal inflection points, we've got two possibilities, this or this. And for these, we have definitely a point where the slope of the curve is equal to zero, so that means that we have a horizontal tangent. But you'll notice that in these cases, the tangent just touched the curve and continued on, so it was touching at one point. Here it's touching at one point, but it's a little bit more. It's actually crossing the curve, and that's what makes it an inflection point. We'll see that that has some other significance later on. So the other thing about an inflection point is, whereas for these, the slope changed either side of the point, for an inflection point, the slope is the same. So for this one, we've got positive slope before the inflection point and positive after. And for this one, negative before and negative after. So let's have a look at this in action. We're going to find the stationary points of this cubic and determine their nature and sketch the curve. So we need a way of figuring out basically the slope of the curve either side of the stationary point. And to do that, usually what we look at is simply the value of the derivative either side of the turning point, in terms of it being positive or negative. The actual number is not that important. You have to be fairly careful that there are not stationary points that are close together, so that we might mess things up just a little by going either side of a pair of stationary points. But usually we just consider our stationary point plus a little value and minus a little value. Now I've written it as plus or minus dx just here, but usually you use an actual value and do a calculation. Examiners are pretty doubtful about you just drawing these up as, for example, a positive slope, a zero slope, and a negative slope, because it's too easy to fudge. So let's have a look at this in action. So our first task is to get the differential. So that will be easy enough. 3x squared minus 12x plus 9. And to find stationary points, we know that we want that to equal 0 for stationary points. So we're really just trying to solve this quadratic. Now in this case, if we divide through by 3, that will just make life easier. So we want when x squared minus 4x plus 3 equals 0 to get a stationary point, which means that x minus 3, x minus 1 has to equal 0, and therefore we have our stationary points when x equals 3 or x equals 1. Now we can get the y coordinates of that by plugging back into the original equation here. But for the moment, what we want to do is just to determine the nature of these stationary points. So when we have our value of x and our value of f dashed of x, for the case of 3, then at x equals 3 that we know that the slope is 0. So it will look like that. Now if we just go a little bit more than that, like, well, we might as well go 4, because we're going, we haven't got another point on that side. So when x equals 4, what happens? Well, this would be a positive quantity and this would be a positive. So here we're going to get a positive, which means that the slope will be like that. Now on the other side, let's take x equals 2, so that's between the 1 and the 3, so it's at least to the left of 3. So when x equals 2, this bracket here will be a negative, this bracket will be a positive, so the product of those is a negative. So that gives us that at x equals 3, our turning point, our stationary point, is a minimum stationary point. And if we look at the case when x equals 1, then when x equals 1, we know we've got 0 slope, so that's our horizontal tangent. When x equals 2, we've just seen over here that we've got negative slope, so the line goes like this. Oh, sorry, goes like this. And when x equals 0, so to the left of our stationary point, when x equals 0, we've got a negative times a negative, which is going to give us a positive, so it goes like that. So we're going to have a positive, a maximum turning point. So now when we go to draw our sketch, then we know where the graph turns. So as usual, we can easily find where we cut the y-axis. So we cut the y-axis at -4. So we did that by putting x equals 0 here. We don't know where we cut the x-axis easily because we can't solve cubics. But we do know that when x equals 3, so we're out here at 3, we're going to have a minimum turning point. So let's get the y value associated with x equals 3. So I think that also works out to be -4. So that's our negative value, and at x equals 1 we had a maximum turning point, and when x equals 1 we've got 1 minus 6 is -5, plus 9 is plus 4, -4 is 0. So when x equals 1, the y value is 0. So our curve is going to look like this. We don't know that value there. We do know that one for sure. We do know that that's 0, and this point here is also -4. So that's our sketch of the curve. Now for our next example, we need to find the stationary points and sketch the curve. So first of all, find f dash of x. So that will be 15x to the 4th minus 60x squared. And if we just take, so let's say 15x squared out as a common factor, that will give us that minus 4. And we can then see that we've got a difference of squares there. So 15x squared, x minus 2, x plus 2. So we want f dash of x to equal 0 for a stationary point. So for a stationary point, 15x squared, x minus 2, x plus 2 equals 0. So that happens, of course, when x equals 0, and it happens twice there, so that's a double root. We've come across these beforehand, or a perfect square if you like. X equals 0, x equals plus 2, and x equals minus 2. So now let's investigate these. So I've just started to set these tables up, so let's look at 0 first of all, and we'll look at 1 and minus 1 either side of that. So when I put a 1 into this expression here, then I'll have a positive, and I'll have a negative here and a positive there. So together that's going to give me, what did I say, positive, negative, positive. So I'll have a negative just there, which means that the slope will look like this. And when x equals minus 1, this will be positive, this will be a negative, this will be a positive. So the slope there will also be negative. So this is looking like our point of inflection. At -2, if I look at a point either side of that, like -3, -1, Well, at -1 we've just seen that we've got a negative slope, and at -3, if I put that in here, that will be positive, this will be negative, and this will be negative. So altogether that will give us a positive. So that's going to give me a maximum turning point. And at x equals +2, if we look at 1 and 3, then we've seen that 1 before we had a negative, why I keep doing that, negative slope. And when x equals 3, we've got a positive, 3 minus 2 is positive, 3 plus 2 is positive. So they're all positive, so we've got a positive slope. So you can see we've got a minimum turning point. So minimum turning point, maximum turning point, point of inflection. Now we just put all that together onto our sketch. Now just a little note about our horizontal point of inflection. Sometimes it's called a stationary inflection because, as we said before, an inflection is a point where the tangent actually crosses the curve, and it's also a point where concavity changes. So if we have a horizontal point of inflection, it's a stationary point and a point of inflection because we have a change in concavity and we have the first differential equaling 0. So let's look at our sketch. So where do we cut the axis? Well, we can see that that's at 0, 0. So that's our turning point, our point of inflection here, which is going to go through this point. When x equals +2 and -2, what is our y value? If my arithmetic is right, at 2 the value of f of x is -64. So we've got 2 minus 64. That fits with our concept that we'll have a minimum turning point there, our point of inflection here, and at x equals -2, I think we'll have +64. So up here at our maximum, -2 plus 64. So our curve, let's just sort of do a dot to dot now basically. It's going to look something like that with the point of inflection in here. So when we look at this, we've got our maximum turning point, our horizontal point of inflection, our minimum turning point. The curve is increasing here, it's decreasing here, all the way down to here, and it's increasing here. And at this point here, it's changed its concavity. Like up until here, it was concave up. From this point on, it's concave down. So that's the point of inflection just there. Now for our next question, same sort of skills, just asking them in slightly different ways. So the tangent to this curve is horizontal, which means that the value of the slope is 0. At the point where x equals 4, find the value for a. So as usual, our first step is to find the differential. So that will be 2x plus a. And we want that to be horizontal, so we want y dash to equal 0 when x equals 4. So that is, when x is 4, we'll have 8 plus a equals 0, therefore a equals -8. Okay, our next example. This curve touches the line y equals 2x at the origin and has a maximum turning point when x equals 1. Determine the values of a, b and c. So our maths brain should be telling us that we've got 3 things to find, so we've got to get 3 bits of information. So first of all, it talked about touching a line at the origin, so we know that it passes through the point 0, 0. So 0, 0 has to satisfy this equation. So there's one bit of information, that when x equals 0, y equals 0. So as we go through that then, we've got, if we substitute x equals 0 and y equals 0, we've got 0 equals 0 plus c, therefore c has the value of 0. So our curve is just y equals ax squared plus bx. Now we also know, we'll come back to this bit here at the moment, we know that there's a maximum turning point when x equals 1. So if we get y dash will be 2ax plus b, it has to be a maximum when x equals 1. So that means that y dashed equals 0 when x equals 1. So that's going to imply that if x equals 1, we've got 2a plus b equals 0. Now our last piece of information is about this line here. So if this curve just touches this line, that makes this line a tangent to the curve. So the slope of this line at the point that it touches is the same as the slope of the curve. And the slope of this line is 2. So that's saying that 2ax plus b, which is the slope of the curve anywhere, equals 2 when they touch, and they touch at the origin. So that's when x equals 0. So when x equals 0, this term here is going to disappear, and we're just going to be left with b equals 2. So we know c equals 0, b equals 2. We know this fact up here, that 2a plus b is 0. So that's going to give us, if b is 2, that's going to give us that a equals minus 1. So we've got our 3 values that we're after. As always, it's probably good, if you can, to do a check rather than accept this on blind faith. So if our curve is in fact minus x squared plus 2x plus c, which is 0, then that will become minus x outside of x minus 2. So just be careful about that, our double negatives. So that's a concave down parabola, which is going to cut at 0 and plus 2, so it will look something like that. We can see that there is going to be a maximum turning point when x equals 1 by symmetry, and the line y equals 2x is going to touch the curve just there, have a slope of 2, so that all looks pretty reasonable. So let's go on from here and try the evens from 2 to 12.